Assalamu alaikum students. Today we shall start a new paper, Feb March 24. Feb March 2025, paper 4-2 of A2 chemistry. So starting from the question number 1, question 1, part A. Silver is a metal in the D block of the periodic table. Silver can form compounds containing either Ag plus or Ag plus 2 ions. So explain why silver is a transition element. So basically here we are supposed to give the definition of the silver as a transition element. So this question is repeated multiple times in the previous year. So I'll show you the answers. All right, so students, here was the question. Now for this question, you can have these different answers. We can have element which forms one or more stable ion with incomplete d orbitals. You can also write like this, a d block element that forms one or more stable ion with incomplete d orbitals, element that form one more stable ion with incomplete d subshell or incomplete d orbital. So these are different ways to answer the same question. Now moving our next question. And another option of giving the answer is you can write that Ag plus 2 is the form stable ions with incomplete d orbitals and incomplete d subshell. You cannot write for the Ag plus 1 because in that case that I have to write the electronic configuration for Ag plus 1 because in that case the electronic configuration would have become 3D10 and 4S0. Now 3D10 is basically a complete D subshell. The complete D subshell cannot be considered as a transition element. So in this case, the D is not incomplete. Instead, it is a complete subshell. So that's why Ag plus 1 must not be indicated while giving the answer. You need to express the 2 plus here. Although the whole of this answer is in the bracket form, which means it's not necessary to write which silver are you considering, because the question asks you to give the answer of silver. It didn't ask you to tell one of these two. So it's up to you, but do not write your incorrect chemistry in your answer. Now the next question is table 1.1 gives data relevant to the Born-Haber cycle for silver 1 fluoride AgF. All right, we are given the values for the first ionization energy of silver and the enthalpy change atomization silver, and the enthalpy change of atomization fluorine, enthalpy change formation silver fluoride. Write equations for the standard enthalpy changes described, include state symbols, standard enthalpy change of atomization of silver. So we are basically required to write the equations here. So the equations shall become for enthalpy change of atomization silver is Ag must be indicated in its solid form, and then it must be converted into the atomic form of the silver. So Ag is now converted into its gaseous form. So this is the equation for the first one. Now the second one is enthalpy change formation of silver 1 fluoride. So we should remember that silver fluoride is AgF. Now Ag in this case will be in solid form because we are considering the enthalpy change of formation. When we are discussing the enthalpy change of formation, then all the elements must be present in the standard form. We do not say the gaseous form because if it was considered as a gaseous, then that would have been from the lattice enthalpy. which in this case not. Lattice enthalpy required all the elements in their gaseous form. Gaseous elements, all of them. So for therapy change formation is Ag is in solid form plus fluorine gas, which is already in the gaseous form like this. That must be giving the silver fluoride Ag and F, because the formula is basically silver has Ag plus 1 state and fluoride is already minus 1. So that's why the formula becomes AgF. But to balance this equation, and yes, one more thing, AgF is in the solid form. That's a solid compound. Now I have to write the uh, coefficients. So for fluorine, it shall be 1/2 after. So like this, now this has given me the full form of the equation. Now the next is define lattice enthalpy. So again, this is a repeated question. So I will show you multiple answers for this question. All right, so that's a question, define lattice energy. So these are all the definitions, one from this paper, another from this paper, and third one from this paper. So you can write any of these definitions which will be considered as correct answer. Now the next question. Calculate the first electron affinity AA1 of fluorine using data from the table 1.1. It may be helpful to draw the labels energy cycle as part of the working for your answer. So we are supposed to find the electron affinity of the fluorine from this given table. Friends, I can show you the easiest way to find the answer from my notes. You can see here that this is the formula which we are going to apply here. Delta H lattice is basically delta HF minus delta H1. That's such a simple formula in which the delta H1 is basically considered as the steps involved enthalpy of, like these are all included in the delta H1, which includes the enthalpy of atomization of metal, enthalpy of atomization, it is an ionization of metal, then enthalpy of atomization of non-metal, and then electron affinity of the non-metal. All of these are included within this delta H1. Or you can also consider from here atomization, ionization, and then another atomization and electron affinity. All of these are considered within this one symbol delta H1. And then this delta H lattice is already understood, which is basically the enthalpy of lattice, and delta HF is enthalpy of formation. So I'm going to use this similar formula in my calculation to find out the answer. All right, so the formula which we deduced from the notes was delta H lattice is equal to delta H lattice in standard form is equal to delta HF minus delta H1. That's a simple formula which you just need to learn. Now applying this formula, we have the values of delta H lattice from the table. So if we go back, and this is the table, delta H lattice enthalpy given, value given is given here, minus 95. So minus 955, sorry. And for enthalpy of formation, that's also given the table, which is minus 203. All right, so it's minus 203. Now for delta H1, I'm going to show all the enthalpies here. Delta H1 will include delta H of the atomization, delta H atomization of the since the compound is silver fluoride. So the first part should become the metal. So enthalpy of atomization of metal, which is Ag in this case, plus enthalpy of ionization, enthalpy of ionization for again silver, to make it silver ion, Ag plus. So this is only and ionization energy. It can be also referred as first ionization energy, or you can simply write as ionization energy. Plus the next is the atomization of the non-metal part, which is in the fluorine in this case. So enthalpy of atomization of the fluorine. So it will become F plus the last is the electron affinity of the fluorine. So enthalpy of electron affinity, which in this case is written as 1, and we have to produce only one, which is fluoride ion in this case, like this. So these are all included within this delta H1 part. Now we are given some values here. The value of atomization of silver is given in the table, which is plus 289. So I'm going to write out just below it. Plus 289 value is given for this part. Then ionization energy of silver is also given. That is plus 70 plus 732 plus 732, and then atomization of fluorine is also given in the table, plus 79 plus 79. But this is not given, so I'm just going to write X over here. Okay, now the next part is we have to do the calculation. So when you calculate it, minus 955 is equal to minus 203. Now you have to add all of these. When you will add them, you will get plus 100. That's the value you will get from here. And then add it with the minus 203, since the value outside is bracket plus X. Now this will become minus 203 and minus 1100 minus X. So this will become 1303 minus 1303 minus X, and you just switch it to the left side. X will be switched to the left side and minus 95 is switched to the right side. When you do this, X is equal to minus 1303 plus 955. So the value will become minus 348. So that's the final answer, minus 348. Now the next question, use the data in table 1.2 to calculate healthy change of solution of AgM. So again, some more calculations are required here. Now again, the solution to the question can be calculated from this formula, which is again a simple formula, delta H lattice plus delta solution is equal to delta H hydration. So we are supposed to find the value of delta H solution in the required question. So I'm going to answer the question. All right, so applying the formula here, delta H is delta H lattice is equal to delta H hydration plus, or you can rearrange the equation delta H hydration minus delta H solution. Simple, because previously it was lattice plus solution was equal to hydration. So I will just rearrange the equation. Now the hydration is given for silver ion and fluoride ion. So I'm going to add them together here. So for hydration of Ag plus hydration for fluoride ion, and then minus it from the solution, delta H solution. Okay, put the values here. Delta H lattice is already given, which is minus 955. Hydration of silver ion is minus 464. For the fluoride, it is minus 506, like this, minus from solution. That is unknown, because we are supposed to find this value. Now you do the calculation part here. The minus 464 and minus 506 will become minus 970 minus x, and this is minus 955. So the value of x will become minus 15. So that's the answer, minus 15 kilojoule per mole. Now the next question. Use the answer to C power 1 to suggest whether AgF is soluble in water at 290 Kelvin. Explain your answer. So we can see that the value for enthalpy of solution was exothermic value, but the value is too small. For a compound to dissolve in water, the enthalpy of solution must be exothermic. It should be exothermic, but again, it should consider the value of the enthalpy. Since the value is too small, so we can say that AgF is slightly or partially slightly soluble in water. Yes, it is slightly soluble in water. Because why? Because you have to just whether and you have to explain it as well. So it is slightly soluble. Yes, it is slightly soluble. That we have given the answer to this part to suggest whether this part is already answered here. Now, what about the answer of the explain part? The reason is that because enthalpy of the solution is slightly exothermic, or you can also say negative. So that's how we can determine that it is basically soluble. Is slightly exothermic like this. So it is, that's why it is slightly soluble. Now the next part is table 1.3 shows some data relevant to silver 1 chloride. Explain the trend in the first electron affinity of the halogens chlorine to iodine. Now, if we look at the table for silver chloride to silver iodide, and the next question, the electron affinity of halogen is decreasing and lattice enthalpy is also decreasing. We had to explain the trend of the electron affinity of halogen. So we can see clearly that the value is decreasing as we move from the top of the, not the top, but the second to top halogen atom out of 7 to iodine. So which means if we move down the group 7, if we move down the group 7, then the value is decreasing. It decreases value. So why we had to explain the reason why it decreases. So as you know that the size increases of the halogen atom, then the attraction between the nucleus and the electron decreases, and that makes it less electron affinity decreases. So the size is basically related to the attraction between the electrons and the nucleus. For this case, so we will write the answer like this. That greater is the distance between the nucleus and the shell of the electrons, or in other words, the atomic radius increases, or atomic size increases, or there are more shells. or there is more shielding by the inner shell. So all of these are considered to be of 1 mark. These are all of 1 mark answers. And then the less attraction between the nucleus and protons and incoming electron added. So you have to focus on the attraction as well. The attraction between the nucleus, or you can say protons, and the incoming electrons or the electron added. That's for the second one. So that's all. 2 marks are completed here. Now the next question, explain the trend in the lattice energies of silver 1 halide AgCl2 AgI. Okay, so why the lattice energy is decreasing? If we look at the table, then as we move down the group, we can see enthalpy values decreasing now. We have to explain the trend, do not state the difference here. Do not state the trend here. They are not requiring you to give state, because state means you will just write down that the value is decreasing down the group, or enthalpy of lattice enthalpy or lattice energy is decreasing. No, do not give answer. Do not write this in your answer. You have to explain why. So again, the reason is that if we move down the group, the size of the halide ion is increasing. So we will write that halide, or you can also write that X minus ion is increasing in size. So when the size of the halide ion increases, or it gets larger in size, or we can also write like gets larger, because both mean the same thing. They gets larger, and as a result of this, there is a decrease, and there is an decrease attraction between the ions. Decrease attraction between the ions. Now the other ion is basically the silver ions. The attraction between ions is called as ionic bond. So you can say decrease ionic bond between the ions because of the increased size of the between the ions, or right, weaker ionic bond. So you know that size is increasing, so there is a weaker ionic bond between the ions. Ion of silver with the halide ions. Now the next question, number E, an electrochemical cell is constructed using the electrodes. So this is a table. We have to calculate the cell potential, and also we have to write the equation for the overall cell reaction. So basically, if we look at the table, we can see that the electrode potential value for the first electrode is plus 0.222, and for two, like electrode 2 is plus 0.342, which means one of these is the cathode and the other one is anode. So the one which has the smaller positive value, it has smaller positive value, it should become the anode. So this is the anode over here. And the one which has a higher positive value will become cathode. That's always a rule. So this is the cathode part, which means we will now use these values, and we will use a equation for E naught cell, which you know as E naught of cathode minus E naught of the anode, or you can also write E of the right hand side minus E naught of the uh, left hand side, or E naught of the uh, reduction minus E naught of the oxidation. So all of these formulas are applied here. So I'm just going to use any one of these that will give me the similar answer. So E naught of the cathode in this case is plus 0.342. So I will write plus 0.342 over here. And then the value for the anode in this case is plus 0.222. So minus plus 0.222. Now the answer will come out to be plus 0.222 1 to 0, and it should keep in mind that the answer should go with two significant minimum. It should be a minimum answer of two significant figures. All right, two significant figures, and that's we have the two significant figures over here. 0.2 minimum two significant figures. Okay, so the answer is plus 0.120 volt. Now the equation, how do we construct the equation? Now we have considered that this is the cathode, this is the cathode part, and this is the anode part, which means the anode reaction should not be written in this way, because you can see here it is written in the reduction reaction way, which is now incorrect, because actually it was the oxidation reaction, not the reduction. That's oxidation reaction, not the reduction. So which means I will need to reverse this equation, and I need to write like this in the opposite manner. In this case, this will become reactant and this shall become product part. So I'm going to write in the similar way, Ag in the solid form plus chloride in the aqueous form, and it should go in this direction. Now AgCl is the product now in this solid form plus electron. And for the other equation that was already mentioned here, copper equation, that should be remain as such since it is a cathode part or reduction part. So copper plus aqueous ion and two electron like this. And so on the right side, you have copper solid. Now, the problem over here is that we have two electrons for the copper side and there is one electron for the AgCl. So these must be balanced, which means this second equation must be multiplied with 2. Only then the electrons will be cancelled from each other. Because for the overall equation, you do not write the electrons. Electrons are always cancelled. They are not shown in the equation, overall equation. So if it is multiplied with 2, it will become 2 Ag plus 2 Cl negative. Then it will go like this, and it should become 2 AgCl like this. Now I have to check these two equations, the copper equation and AgCl equation like this. So the electrons are cancelled now. Two electrons were cancelled from here. And in fact, the two electrons which I should write here, two electrons are cancelled from here. And no other species is there which can be cancelled because all of them are different from each other. So I will write them in the final form. These all come to the final form. This copper will also go to the final form. This copper solid goes to the final form. So the equation should become 2 Ag plus 2 Cl negative and then plus 2 copper ions, not 2 copper ions, just copper plus 2 ions, and then arrow, and right side should have 2 AgCl and then copper like this. So this is the final equation of the question. Now the next question, in a different experiment, electrode 1 is set up using a saturated solution of KCl. Saturated KCl have this mass of KCl per this volume solution. The next equation is given. Calculate electrode potential E of the electrode potential of electrode 1. Sorry. Now, in this question, we are given this information about the KCl, and we are supposed to find the electrode potential E at non-standard condition for chloride ion. So we can see that if saturated solution of KCl aqueous there, which means it contains a Cl negative. So from this KCl value or this mass and volume of the KCl, we can definitely find out the electrode potential of the Cl negative. All right, so how can we do it? First of all, we need to convert this mass and this volume in cm cube into the mole per dm cube, because you can see here that these K brackets indicate that concentration is mole per dm cube. So mass, so the gram in cm cube must be converted into mole per dm cube. So for this purpose, we first do the calculations. So the mass of KCl given is 36 gram. But the MR value of KCl then becomes, for potassium, it is 39.1. For chlorine, we have 35.5. So when you add them together, you will get 74.6. 74.6. Now convert this value into the mole. So number of moles of KCl then becomes 36 divided by 74.6. And so the answer becomes 0.48. 0.48257. I have used as much decimal points as I can. This is the mole. Now this is the mole which we have got for 100 cm cube. So I will write simple relationship here. That 0.48257 mole was obtained when the solution had 100 cm cube. But we are supposed to find the solution, the concentration in 100 cm cube, because you know that dm cube means 1000 cm cube. So for 1000 cm cube, it shall become x. So do the cross multiplication. So x shall become 1000 times 0.48257 divided by 100, which means this 100 is cancelled out. So it will be multiplied with 10 and you will get 4.8257 mole. So this is the amount of the mole per dm cube. So this is the concentration of the KCl in mole per dm cube. Okay, we have calculated this value. The concentration Cl negative is done. Now what about Z? We are supposed to find the Z as well, which you know is the number of electrons in redox reaction. So both oxidation and reduction reaction is considered here. Now we have KCl in this saturated solution form, which means K positive is there and Cl negative is there. And from here, when electrolysis were done, we got potassium metal in this solid form, and then chlorine gas is also supposed to be obtained here. Chlorine in the gas form. Now, it means that we must split this equation into two parts in the oxidation and reduction form. So positive ion was basically gained one electron in the cathode part to get reduced into positive metal, and the chlorine negative was basically lost its one electron in the anode. This is for cathode reaction, and the other one will be for anode. So Cl plus electron. This was done at the anode part. So in both of these cases, we have one electron each, which means the Z is basically equal to 1, since it is 1 electron. So we have got the value of 1, the Z as well. We have got the value of complete. Now we are left with the value of E naught. Okay, now E naught is basically the standard potential. Now, the standard potential is applied for KCl. Now, if we go back to the previous question, we can see here that previously in previous experiment, there was AgCl present, which means the Metal part was different, but the Cl was still the same. The Cl was there, so it means it contained the Cl negative. So definitely whatsoever electropotential, standard electropotential was given for AgCl, it must also be given for the same KCl compound. So AgCl and KCl will have the similar E naught values for the chloride part. So I'm going to apply the same value here, that E naught for Cl negative will be plus 0.222. So this is the value for chloride part as well. Okay. Now apply the formula. E is equal to E naught plus 0.059 divided by, okay, I'm going Z is equal then log of 1 over chloride in concentration form. Supply, put the value, say E is equal, E naught value is plus 0.222 plus 0.059 divided by 1 into log of 1 over concentration is 4.8257. So when you do the calculation, you shall get the answer as plus 0.182 volt. So this is the final answer, plus 0.182 volt. Now question number 2, part A. Question 2, propanol, which is CH3CO. CH3 is a common organic solvent and reagent. Propanol reacts with methanol under acidic condition to form compound A as shown. Reaction 1 is this figure. The overall order of reaction 1 can be found by studying experimental data, and table shows how the initial rate of reaction are weighted. So we are given this table, and we have the relation between the concentration of methanol and concentration of hydrogen ion or acid with the rate of reaction. So part 1 says, explain why a large excess of propanol is used in each experiment. All right, so if the table is indicating the relation between the concentrations of the methanol and acid with the rate of reaction, which means that one of the reactant, which is propanol in this case, is made constant to check the rates relation with the other two reactants. So we could say here that the CH3 or propanol concentration remains constant. Concentration of CH3CO, CH3, which is propanol, remains constant. So we could say this, or you can say does not change, does not change. Or you could also say that the concentration of this propanol does not affect the rate of the reaction. Does not affect rate. So the rate should not be affected by propanol. Now, second part is use the data in table 2.1 to determine the order of reaction with respect to methanol and hydrogens, and then you have to explain. Now, the next part is use the data in table 2.1 to determine the order of reactions 1 with respect to methanol and with hydrogen ions. So basically, we need to do some technical calculations here to find out the right answer. Now, to make it easier, I will first use the concentration. I will first find out the order with respect to the hydrogen ion, since where you can see here that methanol has two values which are totally constant. So these two values make it easy for me to find out the relation between the hydrogen ions and the rate of the reaction. So for experiments, you can see there for experiment number 2 and for experiment number 3, the methanol the methanol concentration is constant. Now we'll look for the hydrogen ion. If you consider here that the value has been changed from 0.05 to 0.020, so I will write that for hydrogen ion, the concentration change is 0.020 divided by 0.015. Now, this is basically, if you see, you can simplify it by dividing it with 4. So when you divide with 4, you will get 4 over, or you can divide with 5, then you will get 4 over 3, which is basically equivalent to 1.33. Now, this is equal to this value, 4 over 3. Now, you have to check the change in the rate. So the rate has been changed from 2.25 to 3. So for this purpose, you will die and do the same calculation, 3 divided by 2.25. Now, if you get this value, find this value, it is now basically equal to 1.333, which means that the value has been changed in the same order. The value has been changed in the similar manner, or you can also write it like 4 over 3, because both has given the same value, 1.333. So in other words, I can say that with respect to hydrogen ions, it is first order. So first order with respect to the hydrogen ions, this is the answer to this part, determine the order of reaction. With respect to the hydrogen ions, this is the answer to this part. And then for the second part, which says that explain, which means I will change the color. For explanation part, you have to answer. The reason is that rate is changed. You can use the symbol X. The rate is changed by a factor of 4 over 3. Rate was changed by a factor of 4 over 3, this value. Or you can also write instead the rate has been changed by 1.33 or 1.33 when and the concentration of hydrogen ion was changed by 4 by 3 or 1.33. So basically you have given the explanation that why it is of first order, because the rate changes by 1 by 33 or 4 by 3 when the concentration is also changed by concentration of hydrogen is changed by the similar value. So this is now calculated. Now we have to find out the relationship of the methanol with respect to rate of the reaction. So I'm going to raise all of these parts so to make it easier and visible for the methanol. Now here, for this case, you have two different approaches to find out the answer. The first approach is to use the experiment number 1 and 2. For experiment number 1 and 2, the concentration of methanol is changed from this value to this value, and similarly for hydrogen ion to this value. Now, if you check, this is the first strategy, and the other strategy is that you can either choose experiment 1 and experiment number 3, because for this case, the value has been changed from 0.01 to 0.015 for methanol, and for hydrogen ion is changed from 0.01 to 0.0. So first of all, I will use the second approach, and then I will go with the first approach, which means I will first check out the red portion. Now for red portion, the concentration, the rate has been increased from 1 to 3. All right. Now we know that the rate has been increased. Rate is increased by 3 times for red portion. I have to, okay, I'm going to raise this part first. So the rate has been increased by 3 times. Now at the same time, the hydrogen ion concentration has been increased by 2 times. On the other hand, the concentration of the methanol, how do we find that? How much is its change? Again, same calculation, 0.015 divided by 0.01. This will give you 1.5. So when methanol has been increased by 1.5 times. So rate was changed by 3 times, whereas hydrogen was increased by 2 times and methanol changed by 1.5. We know that with respect to hydrogen, it is first order. It is already a first order, but we do not know about the methanol. So I can say that the value of 3 can be obtained by this way, that I have 1.5 times 1.5. 1.5 into 1.5 will give me, no, not this way. 1.5 into plus. I will write plus because I have to make it 3. So 1.5 plus 1.5. This has given the value of 3, which means the rate has been increased by 3 times when the methanol was increased by 1.5 times. And in fact, the order of with respect to hydrogen was first order. So I can also consider that the overall 3 value was also obtained when the rate of the reaction with respect to hydrogen was also 1 order was first, but the factor is 1.5, which means it is associated with the first order. So from here, I can say that both of the reactants has provided the first order. It has first order, it has first order. The first order this could be for hydrogen ion and this will be of meth. So both are providing first order with respect to the rate of the reaction. So this is one way to find out the answer. So first order with respect to the methanol. So first order with respect to concentration of ethanol, this is the answer to part 1, determine. And then reason, because the rate is changed by a factor of, the rate was changed by a factor of 3. The rate was increased by a factor of 3. Rate was increased by a factor of 3 when you can say that 1.5 times 2 also gave the answer 3. So 1.5, one part of the 1.5 comes from the hydrogen ion and the other part of the 1.5 comes from the methanol. So this is how you can give the answer. So hydrogen ion has given first factor, one first order, and the methanol has also provided the one order, first order. So the other way around is to consider the other 2 experiments. Now for the 2 experiments, I will use the other way out. Now here in this case, I'm going to use experiment number 1 and 2. Now in this case, the rate of reaction has been changed from 2.25 1 to 2.25, which means 2.25 divided by 1 will give you similar value, which is 2.25. Now in this case, the change in hydrogen ion is 1.5 times, and similar for the methanol 1.5 times. The hydrogen ion is changed by 1.5, meth is changed by 1.5, but the order reaction is 2.25. Now what do you consider here? That we can suggest that the square of 1.25 is also equal to 2.25. 1.5 square is equal to 2.25. So if the concentrations are changed by equal values and they give a similar rate of reaction, then it means that both are first order. Both have provided equal ratio with the rate of the reaction. So again, it is first order. So instead of writing this statement, you can also write because you will write methanol, or you can also write in this way that CH3OH was changed by a value of 1.5, and hydrogen ion was also changed by a factor of 1.5, and rate was changed by 1.5 square. So that's how you get, but you have to refer to for experiments 1 and 3, and for this case, experiments 1 and 2, 1 and 3. For this is experiment number 1 and 2. So you have to give reference to which experiments you are referring to. So that's how you get the answer. Now, question number 3. In a separate experiment, a large excess of methanol and hydrogen ions are added to a solution. We have this graph which shows the concentration or the amount of the propanol, which is decreasing with the passage of time. Use this figure to show how, under these conditions, reaction 1 is first order with respect to propanol. All right, so if you remember from the literature that it is a first order reaction only if the it is first order if the half-life of the concentration versus time gives you equal values. These are from my notes, and you can get these notes if you contact me separately on my WhatsApp number or my email or in the comment section. I can provide you these notes of the kinetics and all the other chapters of the A2 chemistry. So basically here, you can see that the half-life for the first order is same. You can see the value is same for both sides. You can have an idea from here, you can have an idea from this already attempted part. But for zero order, the half-life gets smaller. For zero order reaction, the half-life gets smaller, and for second order, the half-life gets larger. So this is the difference between zero order, first order, and the second order. So in our question, we have to find that the like propanol was first order, which means we need to calculate the half-life values of the propanol. All right, now let's do the calculations here. So this is the y-axis, which indicates the percentage of the original concentration. So this side is basically indicating the amount of the propanol. Okay, you know that for a half-life time, the amount of the substance is decreased by 1/2. It decreased by 1/2. So if I start from the 100% over here, I need to have the other value of this propanol at 50%. So 50% is here. Now for this purpose, I need to check that on which point on the x-axis it touches. So 50% is here at this point. Now I need to find where it coincides on the x-axis. So it is meeting over here. All right, now this is my first half-life. So if I check, this value is basically equal to, this is 10, 20, 30, 40, 50, which means this is 150, 160, and 170. So this value is coinciding at 172nd. What the time is in second. Now, this is my first half-life. So starting from here, 0 to this point is 172nd. This is my first half-life, indicated by this. Now, for the second half-life, I need to have the 50% of this 50%, which means it should give me 25%. The half of this 50% is at 25%. Now this is 25, this is 21, this is 22, 24, 26, 28, 30. So 25 is over here. Now if I check this on the graph, it should give me the value right over here. Now this is the point where I'm getting. And again, I need to check it on the x-axis. So it should give me value over here. This is the value. If I check it on the x-axis, it is 310, 320, and this is 328. Let's suppose this is 328. So I need to find the half-life up to this point from here. So the half-life starting from here, because this is the time when I got the remaining 50% of the amount. So the half-life of this will give me 328 minus 170. The answer is equal to 158 seconds. So 158 seconds are basically, you can see 170 and 158, they are not a big difference. They are almost a difference of 12 seconds. So we can say that roughly the half-life is same. So two half-lives are giving the answer. You can say that two half-lives lie within the range of 170 second and 158 second. So they are and are roughly constant. These values are considered to be roughly constant because there is no such a large difference. So two half-lives are basically same. Now the next question, propanol also reacts with acidified cyanide to form the hydroxynitric compound B, which is given here. And this is the reaction. The following rate equation is determined. This is the rate equation of here. Four possible mechanisms are provided in this table. Okay, so these are the four possible mechanisms. Suggest which of these mechanisms consistent with the rate equation for reaction 2. Explain your answer. All right, now here we have to decide which of the four given mechanisms are which one of the four of these four is the right one. So basically, if you look at this rate equation, we have two species only, 1 and 2. And if you look at the chemical reaction over here, you can see you need to combine these two information with each other. Only then we will be able to determine the mechanism. So I'm going with the first equation first. First mechanism. The first mechanism, other rule is that if you have fast step coming before the slower step, then the species which are present in the faster step can also be included in the rate equation. So the species of the reactant side can be included in the rate equation if the fastest step comes before the slow step. So applying this rule, we have to decide whether the first mechanism is the right one or not. So the first step says it has propanol and hydrogen ions. That is correct. We have these two ions present here. And this is the intermediate. Now this intermediate goes to the slow step where it is totally cancelled. That is fine because we do not have this species present in the rate equation. So that's why it is correct up to this point. But the problem is that the slow step also contains a cyanide ion. Now cyanide ion is nowhere here. It is nowhere here. So you cannot say that this is a proposed mechanism because cyanide ion must not be there in the slow step. In fact, this cyanide is not cancelled with the cyanide in the reactant side of the fast step, it should be cyanide here, cyanide ion here, which should be cancelled with each other over here. But since they are not here, which means it is not the right mechanism. So one is crossed out. Now we go with the second mechanism. The second mechanism says that we have the hydrogen ions in the first step and we have the cyanide ion in the first step. That's fine to give the HCl. So hydrogen ions can be considered in the first step because we have hydrogen ion over here. But again, the problem is with the cyanide ion. The cyanide ion is present in the reactant side, which is not in the rate equation. So rate equation does not show the cyanide ion, which means it must have been cancelled out with the cyanide in the slow step. Also, you can see here that the HCN is mentioned here in the slow step that can cancel with the HCN present in the previous step. So because previous step is in the HCN has in the reactants and the product side, whereas in the slow step it is present in the reactant side. So that is fine. But the cyanide ion is not cancelled out here. So that's why it is not the right answer. It is not the right proposed mechanism here. Okay, now then next is third. In the third mechanism, the slow step contains the cyanide ions. All right, now the difference here is that now faster step comes later than slower step. So no species in the fast step would be considered in the rate equation. They will not be considered here because the faster step comes later. Now slow step has the cyanide ions, that is fine, but where is the hydrogen ion? One more thing, not a cyanide ion. It is not fine because cyanide ion is in this case is present. The cyanide is present in the slow step. Again, the problem is with the cancellation of the cyanide ions. We cannot cancel cyanide ion with a species in the faster step. So cyanide ion uh, is not a species present in the rate equation. So it is not the right answer. And there is no hydrogen ion in the slow step. It should be there in the slow step because that must be the part of the rate equation. So it is not here. So that's why 3 is also cancelled out. Now we check the last proposed mechanism. The last proposed mechanism shows that slow step contains the propanone of this rate equation and the hydrogen ion of the rate equation. That is fine. And this is the intermediate step. This intermediate step is now cancelled with the faster step later on. So you will now have both the reactants of the rate equation and also the cyanide ion of the rate of the chemical reaction. Chemical reaction has cyanide ion but not in the rate equation or rate law. So they are there and the product is there in the fast step because no species must be mentioned in the whole mechanism which is not present here. All of these must be present in the mechanism either slow or fast. They all should be there. But the one which is not present in any reactant side or product side should be cancelled out during the mechanism. Just like this one, it was cancelled with this one because it is not the right answer. It is not the species which is present in the chemical reaction here. So that's why it was cancelled. So looking into all these factors, we can now consider that proposed mechanism is 4 over here. Now the reason, you have to give the reason. Number one reason you have to explain, sorry. The explanation is that the slow step in the proposed mechanism 4, the slow step contains, only species from the rate equation, only species from the rate equation, or you can also say contains the CH3, COCH3, and hydrogen ion from rate equation. You can either write first statement or the second statement, and also the number of moles of the species present in the slow step, they are also coinciding with the rate equation, because rate equation said it is first order with respect to this one and it is first order with respect to this one, and that's why so rate equation, the rate equation should be there in a similar manner. So both of the reactions are 1 mole each. So you will need to write here stoichiometry or moles, mole ratio or amounts corresponds to order of reaction or to the rate equation. That's all. Now the next question, C part, carboxylic acid C, which is this compound, molecular formula, forms when B is hydrolyzed under hot condition, acidic condition, draw the structure of C. Okay, now the B is here. This is the B compound and it must be treated with a hot concentrated acid. So hot acid condition, which means this compound when treated with a acid basically converts these cyanide ions through hydrolysis reaction into the COOH. This is the only conversion here. None of the methyl groups or the alcoholic group will be affected. They will remain as such because there is no attack of the hydrogen ions on these groups. So this is from the AS part because we have already learned these reactions in the AS as well. So I will simply draw the structure, but only by replacing the CN part with the COOH. So CN part converts into the COOH part, and then OH remains there, the methyl group remains there, and the other methyl group remains there. They are intact. They said that draw the structure, which means they are not referring to the displayed or skeletal. So it's up to you. You have your own choice to draw the structure in these manner, but do not write in the form of the molecular formula or empirical formula because that will become incorrect answer. Now the next part is the pK of C is 3.95. Calculate the pH of this concentration solution of C. Show your working. Okay, now they are referring to the pK calculation. Sorry, they are referring to the pH calculation. Well, the pK value is provided and concentration is provided. The solution C is basically the carboxylic acid. You can see here, this is the carboxylic acid. In fact, it is containing both the alcohol as well as carboxylic group. Both functional groups are there. But the reference is to the pKa, which means they are referring to the acid nature of this compound. So which means we are supposed to find pH. Now, you can see here that this is basically the organic acid. It is an organic acid, and we know that all the organic acids are weak acids. That's clear. These are weak acids, whereas strong acids are basically the mineral acids. For example, we know about the HCl, we know sulfuric acid, nitric acid, etc. These are all strong acids. So which means we have to consider the formulae which are associated with the organic acids. Okay. But Before that, you have different formulas which you are going to use here. You have the formula of pKa, which is pKa is equal to minus log of Ka. And then another formula which is going to be associated with the pH of the weak acid. For that purpose, I'm going to show you my notes. All right, from in my notes, again, you can get these notes and PDF form. You can get an access of this Google Drive. So here in this notes, you can see that the formula for the Ka of the weak acid or the pH of the weak acid is this formula. HKa is equal to hydrogen ions concentration square divided by HA. This is the formula which we are going to use in our case. So the formula becomes Ka is equal to square of hydrogen ion concentration divided by the concentration of HA. Now this HA is basically indicating the acid. This is the next formula which we are going to apply here. And lastly, another formula which we will apply is pH is equal to minus log of hydrogen ion concentration. So we will apply these three formulas to find out the answer. So number first, the one formula which we know here is pK minus log of Ka. We convert this formula to find out Ka. So Ka is equal to the anti-log of the, it becomes the anti-log. So for that purpose, I will write, and this minus becomes the power. So Ka will now become Ka is equal to, we have to apply the dialog of 3.95. So it should be written like 10 to the raised power minus 3.95. This is how we write anti-log of the Ka. The anti-log of the pKa, because previously it was pKa, but then we converted into the Ka. For that purpose, the log converted into the anti-log. So anti-log of 3.95 along with a negative sign, because negative sign was there in this formula. So when you calculate this value on the calculator, you should get 1.122 into 10 to the power minus 4. Now this is the answer of Ka. All right. Now we have completed the use of first formula. It is now done. Now we go with the second formula. Sorry, this is the second formula and this is the third formula. Now we go with the second formula, which says Ka is equal to square of Ha, square of Hi. Now, I have to rearrange this equation to find the value of hydrogen ion concentration. So hydrogen ion concentration will then become Ka times concentration of the acid, which is the compound C. C is our acid here, so instead I can write Ka into concentration of the C. All right, so Ka value is given 1.122 into 10 to the power minus 4, and C is the concentration. Now the concentration of C is given here, which is 0.5 mole per dm cube, so 0.5. Now when you calculate this value, you should get, along with that, you have to use a square root as well, because this answer is in square root. So apply square root over here, square root over here. So when you apply the square root here, the answer this part will become 7.49 into 10 raised to power minus 3. Now this is the answer up to this point where this value belongs to concentration of hydrogen ion because we have already taken the square root. Now after this you will apply the third formula which set pH is equal to minus log. So simple pH will then become minus log of the hydrogen ion concentration which is 7.49 into 10 raised to power minus 3. So when you do this, the value shall become 2.13. So minimum significant figures are 2. Minimum significance are 2. So 2.30 is your final answer here. Now the next question, C can be used to form buffer solution. D, define buffer solution. All right, now this type of definition is again a repeated question. So I will show you multiple answers of this question. Right, so here's the multiple answer to the same question. You can write like this: a solution that resists minimize positive change in pH, or when small amount of strong acid or base are added. You can write solution which resists change in pH when opposite which is change in pH. When a small amount of acid, hydrogen and alkali base are added. There is a mistake here in pH. This is not whenever right now. In pH or you can write resist change in pH. And another option is a solution that resists opposite minimize change in pH when a small amount of acid OHI and base alkali hydroxides are added to it. So these are the multiple answers to the same question. Now the next question, 2, buffer solution D is made when this volume of NaOH and concentration is added to this volume and concentration of solution C. pK is given, calculate the pH. All right, now first of all, we need to calculate the 20 cm cube of 1 mole per dm cube. Now this is basically equivalent to the 0.02. This is equal to 0.02. So these are the moles of NaOH which were used here, 0.02, and the moles of the solution C. Now you remember that C was basically this acid. This is C. And acid must be reacting with the NaOH. So the volume for the acid should be calculated from here. We have N is equal to C into V over 1000. So this should give you 0.05. Now these are the moles for C. We have calculated the moles of both the NaOH and C. Now you remember that the reaction is between the acid plus NaOH. Now this is the reaction, which means that the amount of the acid has been decreased by reacting with the NaOH. NaOH amount came out to be 0.02, which is less amount, and the acid amount was 0.05. Now it says use the formula for the pKa. Now for the formula of buffer, I will show you my notes again.